Okay, to start here in this video, we're going to formally define independence of path for a vector field. So if f is a continuous vector field on the domain D, and it's true that for all piecewise smooth curves C1 and C2 in the region D with the same initial and terminal points, the corresponding line integrals over those paths are equal, then we say that the line integral is independent of path. Okay, and when we looked at the fundamental theorem of line integrals, we noted that one of the big consequences of the theorem is that if you have a conservative vector field, so in other words, f is the gradient of some function phi, okay, then this line integral will be independent of path because that line integral then is computed in terms of your potential function phi. You just evaluate at the endpoints and subtract. It does not care how you get from point A to point B. Okay, so what about the other direction? If I know the line integral is independent of path, does that imply that the vector field f is conservative? And it turns out that that is true, provided your domain D is open and connected. So that's the content of theorem 17.5 in the text. It says, let f be a continuous vector field on the open connected domain D. If the line integral is independent of path, then the vector field f is conservative. Okay, so again, provided we're on an open and connected domain D, this condition of being conservative is now seen to be equivalent to the line integral being independent of path, which is quite nice. Notice we're not requiring D to be simply connected. Open and connected is sufficient. All right, so let's look at question 5 then. It says the figure shows the vector field f, which is 2xyi plus x squared j, and the three curves that start at the point 1, 2 and end at the point 3, 2. Explain why the line integral has the same value for each of the three curves, and then it says what's the common value. Okay, and what this question, of course, is getting at is the fact that this vector field is conservative. Okay, so let's first go ahead and verify that it's conservative. Okay, so if I differentiate p with respect to y and q with respect to x, I get 2x for each. And since our domain is all of R2, which is certainly open and connected, and in this case, simply connected, right? So for that test for two-dimensional vector fields, right, the fact that these are equal and we're on a nice domain that's both connected and simply connected, that implies that our vector field is conservative. Okay, so now we got to go about finding the potential function phi. Okay, so if I set f equal to the gradient of some function phi that I'm looking to find, then in particular that says the I component of the field f, so in other words 2xy, that has to equal the I component of the gradient of phi, which is just the x derivative of phi. So I have that partial phi partial x is equal to 2xy. Go ahead and integrate with respect to x to get that phi is equal then to x squared y plus, and this is a constant function with respect to x, right? So in other words, this function c of y depends only on y. Okay, so then to find c of y, we can go ahead and differentiate phi with respect to y, and that's going to give us x squared plus c prime of y. But also note that the y derivative of phi is the j component of the gradient of phi, and so that must then equal the j component of f, which is our function q, right? That's just x squared. All right, so now with this equality, I see I have an x squared here and here, so that then implies that c prime of y is 0. So c then must just be a constant I'll call a. All right, so now we found a potential function phi for this vector field f. It's x squared y plus some constant a. So if I want to compute the line integral along any one of these three paths, all I have to do is evaluate this potential function at these endpoints and then subtract. And when you do that, you get 16. And as I noted in a previous video, this constant a here, we can disregard because when you take this difference, right, it's just going to cancel out. So you just as well could set a to 0. Okay. All right, well, that's going to do it for this video. I'll see you in the next one.